This is just a short video about the basics of input-referred noise. We often quantify the noise of a circuit in terms of its input-referred noise. It's a quantity that represents all the noise sources in the circuit as one or sometimes two sources at the input. So the idea is you have a real circuit filled with noise arising from each and every component in the circuit, but that instead you can pretend that the circuit is entirely noiseless, but there's really just one noisy source at the input. And it's useful because it's usually at the input that your signal is being applied. So it allows the level of noise to be compared directly to the input signal amplitude and to get a feel for how badly that input signal is being corrupted by all the noise sources in the circuit just by comparing it to, just by reference to one number. It also allows different circuits to be compared in a fair way, because a circuit with a higher input referred noise will more badly corrupt a given input signal. We should remember, though, when we make this equivalence, that it's just a model. The input referred noise source Vn in here doesn't actually exist, and there's no noise showing up at the input node of the circuit. All the noise is arising inside the circuit. If you can think of it as the signal proceeds from input to output, it's getting corrupted by more and more noise as it encounters more and more devices as it proceeds down the signal path. But there's not necessarily any noise at all from these sources arising at the input. There may be, but it's not. If there is, it's not directly related to Vn in. Vn in, just describes the effect of all noise sources on the signal as it's passing from V in to V out. And remember that physically we really only have access to these nodes here. This node here is a fictitious node that doesn't really exist and we can't really see it. So a classic example is to consider an RC circuit. If we think about an input voltage source Vs connected to a simple RC circuit, only the resistor here has any thermal noise, and it's modeled by the white power spectral density Vn in that has a power spectral density of 4 kTr. And if we want to find the output noise due to the thermal noise of the resistor, then we can do a small signal analysis setting Vs to 0. Doing so means that we effectively replace Vs with a short circuit. And now we're left analyzing this simple RC circuit here. We've got a white power spectral density. It passes through a first order low pass RC filter. So we end up with an output power spectral density, V out N, that at low frequencies is simply 4 kTr, but that encounters a corner at 1 over 2 pi RC. To find the total output noise, we should integrate the power spectral density at the output, and doing so gives the classic result kT over C. Now for the exemplar values given here and at room temperature, kT over C is the value given here, and we could take the square root of that to find the output RMS noise, which it turns out is about 64 microvolts in this case, RMS. Now, if we want to talk about the circuit's input referred noise, that's pretty straightforward because there's only one device contributing noise, and the thermal noise of the resistor is essentially already input referred. It's the only noise source, and it appears right at the input. So the input referred power spectral density is simply 4 kTr. But we have to take some care in interpreting this, because this white input referred power spectral density suggests infinite input-referred noise, and that's not necessarily the intuition that we're looking for here. And when doing noise simulations, I think it's always great to get your feet wet by starting with a really simple test circuit like this one, and you know analytically, very simply, what the result should be. It should be KT over C at the output. And in fact, there's very few non-idealities at play here. You should get almost exactly KT over C if you set up your simulation properly. So it's good test case because you'll know once you've done the simulation if you've set things up properly and if you're doing noise simulations properly. So if you run a simulation like this, you should see the first order low pass filtered output power spectral density, such as the one shown up here in blue, with corner frequency at 1 over RC. Don't get fooled by the shape of this plot. You note that the y-axis here is on a linear scale, so if this were on a logarithmic scale, you would see the classic first order low pass 20 dB per decade slope there, but because it's on a linear scale, then of course it asymptotically approaches 0 at high frequencies here. And you can also ask simulators to, in general, to plot the input referred noise spectral density, which we already said in this case is white. And indeed, if you set this up, you'll get, if you set this up properly, you should get precisely 4 KTR for the input referred noise spectral density. But again, if you integrate this, it looks like, you've got infinite input referred noise. But at the output, you've got a finite amount of noise. So it's not as though an input signal is being corrupted by an infinite amount of noise here. There's only 64 microvolts RMS of noise being introduced as a signal goes through this RC filter. So that's why I say, some care is needed in interpreting the input referred noise. In this simulation, you can also get the simulator to integrate that output noise spectral density, and the result it gets is in very close agreement with the just back of the envelope calculation for KT over C in this case. So that's good. So what does this really tell us about the input referred noise? Well, this, simple RC low pass filter has a DC gain of 1. So if the input signal Vs is at low frequencies, it sees a gain of 1, and it's corrupted by about 64 microvolts RMS of noise at the output. So, if we're interested in the SNR impact of the noise of this RC network, the noise of the resistor really, then, as long as Vs is within the bandwidth of this RC filter, the SNR impact would be the same as if we superimposed 64 microvolts RMS right on top of Vs. So, if you're calculating you know, the SNR of the signal as it's going through this RC circuit, I mean, I think the right way to think about the input referred noise here is to say that it's 64 microvolts RMS and not infinite, as would be suggested by just integrating the input referred noise spectral density over all frequencies. Now, this circuit was very simple. There was only one noisy component in the circuit, and that was the resistor. But in general, noise simulations can also, if you look at the report produced by them, can be very useful because they will separately identify the noise contribution of each device in the circuit. So this could be very useful in, for example, an amplifier circuit where you may have many transistors contributing to the output noise, but quite often only one or maybe two of the transistor's noise terms are really dominant. So if you want to make a change to design that will have a significant impact on its noise performance, you really want to focus your effort on those particular transistors, and the simulator will help point you to um, which transistors are dominating the output noise. Although hopefully, as the designer, you would already have some intuition as which transistors those might be. As we mentioned before, we have to take some care also in representing all the noise in a circuit with just one input-referred noise source, and that's because the source impedance that we connect in series with that input-referred, in this case voltage noise source, will have an impact on how much output noise results from this source Vn in. So that tells us that we can't just have one input-referred voltage noise source here that will work for any source impedance that is connected. Um, so one way to deal with this is to, in fact, model all the noise of the circuit with two noise sources, a voltage noise source and an input-referred current noise source. It can be shown that modeling all the noise of a circuit with two input-referred sources like this is sufficient to capture all the noise sources regardless for any arbitrary source and load impedances that may be connected to the two-port network. But another way to do so is to simply find the input-referred voltage noise source with the particular source impedance already in place. So if we wish to develop a model for a noisy circuit using two preferred noise sources, a voltage and a current source, we can do so as shown here. The input-referred voltage noise source is found by shorting the input terminals here and finding the resulting output noise, and then referring it back to the input, whereas the input-referred current noise source would be found by leaving these terminals open, that is, setting ZS to infinity, and finding the resulting output noise then and referring it back to the input. And this makes sense clearly because when ZS equals 0, then IN in will have no contribution. All that current will just flow through the short circuit connected to the input and give rise to no noise at the output. And similarly, when ZS is infinity, there's an open circuit here. This voltage noise source will not do anything to these nodes over here. And so the only contributor to the output noise in that case, when ZS is infinity, will be the input-referred current source. For ZS values in between 0 and infinity, both noise sources will contribute, obviously with the voltage noise source dominating at small values of ZS, the current noise dominating at large values of ZS. But when ZS is already known, then only one noise source can be, in fact, either a voltage or current noise, input-referred noise source, is required to produce the correct output noise, as long as you include that source impedance ZS in all the calculations or simulations you perform in finding the input-referred noise current source. So essentially, one input-referred noise source is enough for one particular source impedance ZS. It's when you go and change ZS, then that single input-referred noise source may not be right anymore. And, again, you should note here that unless ZS happens to be 0, then the input-referred voltage noise that you find with ZS in place will not be the same as the one that would be used in the general noise model that includes both input-referred voltage and current noise sources. So in general, the procedure may look something like this. Let's say you've got an amplifier circuit that you're interested in analyzing and knowing something about its input-referred noise. You know that the amplifier is going to be driven by a source with a source impedance ZS and it's driving a load RL. And the amplifier, of course, has a bunch of noisy transistors in it. Well, what you can do is perform a noise analysis of the circuit with Vs equal to 0. If you're doing it by hand, you do the analysis one noise source at a time, and then superimpose them all at the output, or of course you can run a simulation and then an AC noise simulation of this test circuit here. And then what you'll get at the output will be a bunch of noise sources all superimposed, giving rise to some output noise power spectral density like this. And then we integrate that to find the output referred RMS noise squared. We can take the square root of that to find the output noise RMS. Then we can, and since we found that output noise with ZS in place here, we can then find an equivalent input-referred noise voltage simply by taking that output noise RMS and dividing by the midband gain of the amplifier A. And that'll give us the input-referred noise, total input-referred noise in RMS terms, that is captures the noise performance of the amplifier as long as the source impedance remains the same, as long as the source impedance remains ZS. Now, if our amplifier of interest, for example, is a transimpedance amplifier and it's going to be driven by a current source IS, no problem. The procedure looks very much the same. Again, you set the source to 0. In this case, that means open circuiting IS, and you perform the noise analysis, either hand analysis or simulation, with ZS connected to the input of the amplifier. The noise analysis will give an output noise RMS, and that then can be input referred by dividing by the transimpedance gain of the amplifier, in this case Z. Now we can model all the noise of the circuit with a single input referred noise current source I in this case, whose RMS value is the output voltage noise, or in RMS terms, divided by Z. And again, this is a suitable noise model for the amplifier as long as the source impedance ZS doesn't change. So the nice thing about using an input referred currents noise source in this case is that, again, it can be compared directly to the signal current, right? They both have units of amps, so we can directly find the SNR here. And this would be the SNR at the output, in fact, because really remember that this noise is not truly arising at the input. This whole thing is just a model for the amplifier. The noise doesn't really show up until the outputs, but we can compute the SNR that will arise at the output just by comparing the signal input signal amplitude to the input referred noise current in this case. A final example here shows the utility of the concept of input referred noise. Imagine that you've got two amplifiers, one with a gain of 3 and an input referred noise of 1 microvolt RMS, one with a gain of 8 and an input referred noise of 0.76 microvolts RMS. And you need to realize a total gain of 24. So you need to put these two amplifiers in series, but you have the flexibility to put either one first. So, but there's one ordering that's clearly preferable in terms of noise performance, and that can be seen by comparing the two configurations and finding their output noise, right? And you see that in the top example, the 1 microvolt input referred noise of the first amplifier sees a gain of 24 all the way to the output, whereas the input referred voltage noise due to the second amplifier sees only a gain of 8. And remember, you must sum these two noise contributions in the sum of squares fashion, right? So in fact, clearly this is not just 24 microvolts due to this guy plus 0.75 times 8 microvolts due to this guy. In fact, it's 1 microvolt times 24 squared plus 0.75 microvolts times 8 squared. and we take the square root of them all. And of course, the reason is because these are not deterministic signals, they're stochastic signals, so they don't always superimpose constructively, right? I mean, sometimes one noise will be positive and the other noise will be negative, so we don't just add them up linearly. Instead, they add together in the sum of squares fashion because they're stochastic. And we do the same thing for the bottom configuration, and we get a much lower noise at the output. Um, if we take this output noise and input refer it, we would see that it's almost, by dividing this value by 24, we would see that it's almost precisely equal to this value. Similarly, the input referred noise of this cascade of amplifiers is just a little bit greater than 1 microvolt RMS. So in both cases, we see that the input referred noise of the overall cascade of amplifiers is almost equal to and is clearly dominated by the input referred noise of the first stage. And that's because the second stage's noise, when it's input referred to the front of the cascade, gets divided by the gain of the first amplifier stage. This also illustrates common intuition, which is that the noise of the first amplifier stage is the most critical one. All subsequent amplifier stages noise will be attenuated by the gain of the first stage. And so it illustrates why we often use a so-called low noise amplifier to amplify small amplitude signals as the first stage. And these stages are designed to have as low an input referred noise as possible, so therefore they don't corrupt the small amplitude input signal, and should have at least a modest gain, but they may not require a particularly large gain. Their job is just to attenuate the noise of subsequent stages when input referred. So, even a gain of 3, 5, or certainly 10 is usually enough that it renders the noise of subsequent stages almost irrelevant.